All right. Before we get started talking about moment and center of mass, the other physics thing, anyone have any questions about the stuff we did on Tuesday? As far as going about the what did we do on Tuesday? We talked about all the kinds of ways you can do work or the fluid force due to pressure kind of stuff. If anyone has any questions, thoughts, observations, or a specific example they might want me to look at, we could start with that if you wanted, but you don't have to. Well, I'm not seeing any hands. If you decide there is something you really want to see about that stuff, we can certainly revisit it. But we'll talk about moment and center of mass. I should probably write the date first. Today is the 15th in the class, which is Co-21. Oh, there we go. Cool. So yeah, moment and center of mass. So a little bit of context before we get going here. So weight or force, you can think of as being equal to mass times acceleration. Acceleration due to gravity. Typically, the mass is a constant for an object, right? Their mass doesn't change. The acceleration of gravity can change in lots of ways based on your elevation or the planet you're on or whatever. So can be variable. We think you were just stuck on Earth, then okay, fine. So the idea here is that force equals mass times gravity. Or more generally, force equals mass times acceleration. And there's also some other interesting physics equations like force equals the constant times the little mass times the big mass divided by the radius squared. That's the force attraction between two objects. That said, we're going to change it up a little bit. We're going to kind of look at a different situation. So when a force is applied to a lever arm, and we'll talk more about the lever arm in a second, at a certain distance from a fulcrum, a torque results or is produced, which causes the lever arm to rotate about the fulcrum. I often think of a teeter-totter. So you could have something like, now this is going to look kind of weird because we're thinking of our fulcrum as being right here and the total teeter-totter is just on one side of it. And then you're applying some force this way and it's going to make that lever arm rotate around the fulcrum. So it's going to end up going like that, right? It's going to have rotated some amount. And so very generically, we can think of the torque as being equal to the force applied times the distance from the lever arm. All that to say, the moment, the idea of a moment is similar to torque, except that instead of being a force times the distance from the fulcrum, it is the mass times the distance. So that we're not talking about a force times the distance, we're talking about a mass times the distance, but still the same idea is really in play. And the moment is kind of something I'm not great at explaining, but it's the idea of the tendency of something to rotate around a particular fulcrum. when the something is a distance away from that fulcrum. So writing down some words here. Moment is similar to torque. But we use the mass instead of the weight/force. So when we're calculating the moment of an object, moment is equal to the mass of the object multiplied by the distance from the fulcrum, or the object we are rotating around. Often the x-axis or the y-axis. Yeah. It's kind of like the way I kind of think of it is it's essentially the thing you might be thinking about balancing on. So my picture in my head is always a teeter-totter. So you've got this teeter-totter and I'm sitting on it over here, and my 11-year-old niece is sitting on it over here. And since we're both the same distance from the fulcrum and I weigh a lot more than my 11-year-old, or sorry, I have a lot more mass than my 11-year-old niece, this thing tends to rotate that way. The moment is going that way. That's very broadly the idea. And I will again point out, I am not great at explaining this. If you want a better explanation, go talk to Duff. He's one of the physics specialists. He can give you a much better idea of what moment and torque are really about. So I'm kind of okay at explaining it. I'm much better at calculating it. Yeah. Duff, where can we find Duff? Good question. Duff is, I say, so Casey is also a good option, although I feel like no. Duff is maybe a little bit harder to find lately because he's been having some leg issues. I think he's been walking around in a cane. But let's see, where can we find Duff? Let's find out. So if you go to the AATC website, click on physics, and then scroll down here. Basically, I would just go over here to Casey and Duff's websites. And Casey, you can find his schedule right there. He's available at many times and places. And Duff, there's Duff right there doing something with a rocket. Here's his schedule there. So that's when and where you can find Casey and Duff. And they love talking about physics. So you should definitely ask them physics questions if you have them. Also, if you ever have to take probably the Physics 9 series, maybe the Physics 7 series, I definitely recommend signing up for the co-classes. I took them when I was a student here many, many years ago, and they were very, 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 very helpful. Physics is really hard. I think it's gotten even harder here since I took it, and it was hard then. So definitely, if you have to take the Physics 9 series, you might have already started it, or you might be taking 9A this quarter because I think you have to be taking 21B concurrently. Anyway, whenever you start it, or if you started it, get some help because it's hard. So yeah, you can find them. Yes.
Do you know if the class is at the same time every quarter?
I don't know. I feel like it typically is. Well, I should say, I think for physics, it more often is because Casey and Duff have their schedule typically is more rigid. So I think usually the Co-9A, Co-9B, Co-9C classes I think they're usually taught by Duff, and I think they are. I can't say for sure. I think they are. I don't know. I do know when things are going to be next quarter. If you want to know, or at least let me take a quick peek here, just since we were on the subject. Let me find that. Yeah, sure. One moment. Apologies. I know what's much more interesting than talking about moments. Let's see. Where is our schedule here? 1 second. Or maybe not. Maybe I'm a liar. Sorry, we were talking about our schedule. There we go. I found it. Let's see, chemistry, physics. So, oh yeah, there's everything. Wow, that's a lot of classes. So Co-9A in fall quarter should be Tuesday, Thursday from 9 to 10:30. Co-9B, Monday, Wednesday, Friday from 9 to 10. And Co-9C, Monday, Wednesday, Friday from 1 to 2. And you should eventually be able to find these classes on the AATC website. So let me just take a quick look here. So typically, just so you all know, when you go to this website, you click on the thing, you scroll down a little bit, it tells you when and where the co-classes are once we have them scheduled. So here's the spring physics pre and co classes, and eventually, fairly soon, oh, fall right there. So we have and I don't think you have to sign up for them at all, you just go. So the 9A, 9B, and 9C right there. Cool. And they're all in our lovely Dutton Hall, room 3218. Get help with physics. Physics, if you like, physics is really hard. At least it was for me. Maybe some people like it just comes naturally too. Not me. Math on the other hand is great. So back to talking about moments. All right. So what we're really kind of going to do with this eventually is think about the center of mass of an object. So we want to think of the center of mass as the balancing point. A really interesting example of center of mass is how people started changing how they did the high jump. Right? There used to be people like jump the high jump by like going legs like a normal person would maybe jump instead of doing this whole like turning around and arching over thing like that. And the reason they do that is because when your body is shaped like this, your center of mass is down there. So you don't have to work as hard to move that mass to a height. Because the idea is we can imagine that the amount of work done, right? Work is force times distance, and you're moving your forceful weighing body a certain distance. If you can get that center of mass to be lower, then you don't have to do as much work to get it up above the bar. Kind of cool. So let's look at an example though. So here's the question. Yeah, is this a question? Sorry. Right. So we're going to say the following. Let me draw this picture first. I feel like this picture looks really, really funky. Oh, I see. Okay, I get it. Right. So here's my system. Here's my fulcrum. And 1 meter from the fulcrum, we're applying a downward 5 kilogram mass, right? So I know it's not a weight, but fine. And then another 3 meters over here, we're applying a 3 kilogram or setting down a 3 kilogram mass. And then finally, another 6 meters, we're setting down a 2 kilogram mass. And the question is, at what distance should we apply a 10 kilogram mass in the opposite direction so that this whole system balances? So in fact, let me write down the words. So where should an opposing 10 kilogram mass be applied for the system to balance? So for things to be balanced, to quote unquote balance, the total moment needs to be zero. Or in other words, the sum of the moments needs to equal zero. All right, well, we can find the moments. Again, moment at this point is just mass times distance from the fulcrum. So the moment going in the clockwise direction, sorry. So the moment in the clockwise direction is going to be 1 meter times 5 kilograms plus 3 meters times 3 kilograms plus, oh, not 3 meters, sorry, 4 meters, apologies, right? We are 4 meters away from the fulcrum, plus not 6 like I was about to say, but 1 plus 3 plus 6 is 10 meters times 2 kilograms. And we are going to, in the opposite direction, so we're going to subtract, be applying a mass of 10 kilograms times whatever that distance we're trying to find is equal to. And we're going to set that equal to 0 so that the system is balanced. So let's solve for x bar. So x bar, well, if I add this over to the other side and then divide by 10, I can say that 1 times 5 plus 4 times 3 plus 10 times 2 divided by this 10 kilogram mass is going to equal my x bar. Again, I'm just adding that over, subtracting. I will also point out these are all positive because we are going clockwise. And this is negative because it's counterclockwise. So here's what we get. We end up getting that x bar is equal to, let's see, 5 plus 12 plus 20 is what, 37? Divided by 10 is going to be 3.7. So 3.7 meters from the fulcrum is where the balancing point would be. Is where we would situate an opposing mass of 10 kilograms to balance the system. Another way to say that is that 3.7 meters is the center of mass. This system, if we put the fulcrum there instead of over there, that system would be balanced at that center of mass because there'd be just as much tendency to rotate clockwise as there would be to rotate counterclockwise. The reason I picked the 10 kilogram mass here, it might seem kind of arbitrary. It's not. It's a 10 kilogram mass because I was taking the sum of those masses. 5 plus 3 plus 2 is 10. So another way to think about calculating the center of mass is it's the sum of the moments divided by the sum of the masses. That's how we calculate center of mass. And we usually use x bar, like the average of x notation, right? That's what x bar usually means, is the average. That's why we're using that notation, because it's kind of like the average place. All right, so of course it's never going to be this easy, right? We're not just going to be given numbers and distances and asked to multiply things. Of course, we're going to start using integrals because it's calculus. Why wouldn't we use integrals? So let's look at a more typical example. We want to find the center of mass of a thin rod whose length is 10 centimeters with a density of delta, is usually some we use for density here, x squared grams per centimeter, as x is measured from the left end of the rod. So let's draw this little picture here. Here's my very thin rod. And this rod is 10 centimeters long. So we're thinking that over here, that's where x is equal to 0 centimeters. And the density is 0 grams per centimeter, if you like. And over here, this is x equal to 10 centimeters, where the density is 100 grams per centimeter. Grams per centimeter, yeah. All right, so again, if we're trying to find the center of mass, we're trying to find the place where things balance, right? We're trying to find what x bar needs to be. So that, again, the sum of the moments ends up being 0. Or in other words, again, we don't really want to go through that calculation again when we say, all the moments plus the moment in the opposite direction equals 0, and then we subtract and divide. We're just going to go with, hey, we know it's going to be the sum of the moments divided by the sum of the masses. Oh, sure. Sorry, I just had a thought about the previous thing we did, which might be a little bit more elucidating. We'll see if we want to go back here. But now the moments are different, right? It's not just adding up a bunch of finite discrete things. We actually have to use an integral here. So we're going to look at a little slice right here. And we're going to say, cool, for this slice, which is dx wide and x from where we're pretending the fulcrum is, the moment of our strip there, well, it's going to be equal to, just like whatever the moment's equal to, it's always the mass times the distance to the place that we're at. So it's going to be the mass. What's the mass here? Well, mass is going to be the volume or the area or whatever the kind of dimensional thing is times the density. So in this case, the mass is just going to be our little strip dx wide multiplied by our delta. So our moment is going to be our mass divided by our, not our mass, sorry, our mass. So our mass times our distance, which is going to be our width dx times our density delta times our distance x. So we're going to end up getting that the moment is equal to, and then the mass, of course, is equal to just our dx times delta. So then to find the to find the center of mass, we're going to do, well, the total moment is going to be the integral of this. So it's going to be the integral of x times delta times dx from as far left as x equals 0 to as far right as x equals 10. And the mass is going to be the same thing, except we don't have the lever arm in there. So it's just going to be the integral from 0 to 10 of delta times dx. And that's often how I think of it. The difference between the mass and the moment is the moment gets, each thing gets multiplied by how far we are from the fulcrum. So the only real difference between what we're calculating is there's an x there and there isn't an x there. We're going to plug in the values now, or sorry, we're going to plug in the function that the density is equal to. So the density is x squared. So whatever we have going on here, we have the integral from 0 to 10 of x times x squared dx divided by the integral from 0 to 10 of just x squared. The rest of this is not too terrible. We're going to get x to the 4th over 4 from 0 to 10 over x to the 3rd over 3 from 0 to 10. That's going to end up being 10 to the 4th over 4 divided by 10 to the 3rd over 3, which is going to be 10 over 4 times 3 over 1, which is 15 over 2, or 7.5. 7.5 what? Good question. What are we even measuring here? Centimeters, right? We're measuring where the fulcrum should be placed so it balances. So about here-ish, 7.5 centimeters away from the left side, that's where this thing would be balanced, where the tendency to rotate this way is equal to the tendency to rotate that way. So we could actually, I don't think we should do this, but you could reframe it and say, now if I think of it as this is where my fulcrum's placed, I could calculate this moment and that moment and see that they're exactly opposite of each other, which would be kind of interesting. Be kind of a pain in the butt, though. We could have also done it back here, which is actually what the thought I had. Like if we went back to this previous example, we could say, all right, if you put your fulcrum at 3.7, then you could calculate the moment on that side and the moment on that side. But again, kind of terrible. It's actually not that terrible. I kind of want to do it, but I don't think it's the best use of our time. Maybe. Okay. So, yes.
Why is math equal to x dx times the density?
So the mass is equal to so mass is equal to something times density. In this case, since we're talking about like, we're pretending this rod has like no thickness. It's a very thin rod. So the only dimensionality it has is length. So here our mass is length times density. In other problems, it might be mass is area times density. In other problems, it might be mass is volume times density, depending on what kind of object we are imagining. So a lot of the times we're imagining like a really thin rod that has weight, but no kind of thickness at all, really. It's just got length. Most of the time, it's going to be area, though. We're going to say we have like a very, very thin plate, and we're going to talk about the mass of that plate being the area of that plate times the density of that plate. So that's why we have this going on here. So typically, density is your mass divided by whatever the kind of space your thing takes up is. It could be, it's usually mass divided by volume, right? Because usually we think of everything as having a volume. But in math, we like to pretend things don't have dimensions. So we also might say density is mass divided by area, or density in this case is the mass divided by the length. So that's how we're getting mass here as length times density. So bless you. The density here, sorry, the density right here, sorry, the mass is our density times our length of our little strip. Fair question. All right, so let's look at some more interesting examples, or some more typical examples. Yeah. No, I did not yet. So one thing I want to point out as we get into the more typical examples here is the formulas we're about to see are terrible. Kind of. When you take 21D, you'll see these formulas again, except they're going to be so much nicer because there's a whole extra thing you get to do that kind of negates some of the terribleness. So hold on to your hats. Question. I don't think Parlac is covering this either. So yes, so these are the two sections that used to get covered in 21B, like when I took it many years ago, and they updated the syllabus, I think in like 2000, and this content is not in the syllabus for 21B anymore. Sorry, your teacher decided to teach it. Your teacher, or I mean, I should say your teacher, Babson decided to teach it, right? It's on the syllabus. Babson has taught this already, right? Yeah, he's already talked about centers of mass and moments and all that jazz. So, right, if you're in Babson's class, you get to learn more. Lucky you. Yeah. So yeah, right. Academic freedom. People can teach what they want. It's not like he's leaving things out of the syllabus. He's just adding a few things in. So let's find the center of mass of the thin plate. How thin? Extremely thin. Like it has no thickness. Of the thin plate, where'd you go? I'm going to draw it. That is bounded by the curves y equals root x and y equals x. So here's my thin plate. And I should say with constant, or if you prefer uniform, which I think we do prefer, density. So typically, when we talk about finding the center of mass of an object that has a constant / uniform density, there's a different word we use for that. Instead of calling it the center of mass, we call it the centroid, or the geometric center. So one way to think about this is the centroid is where this thing would balance. If you were to like put your finger under the shape and like lay it flat and you could balance it, it would balance exactly at its center of mass, or its centroid. Now, there's some objects that are really easy to think about where its centroid would be. A circle, for example. The centroid of a circle is the center of the circle, because if you could hold it right in the center, the likelihood to swing or tilt one way or the other is going to be 0 because it's perfectly balanced, because it's symmetric. in kind of all the ways. In fact, the circle is like the most symmetric thing you can look at, but it also work for a square or a rectangle. Those shapes, their centers are their centroids as well. So sometimes we abuse the symmetry of objects to make it easier to calculate these things. Unfortunately, not here. So here's what we're going to do. And yeah, so first of all, let's talk about how we're going to calculate this. So for thin plates, the way we're going to calculate the centroid, which is a point in the plane, doesn't actually have to be in the region. It could be down here. It's probably not, but just like the person jumping over the high jump kind of example, sometimes the centroid of an object can be outside of the object, or the center of mass of an object can be not contained in the object, which I think that's really neat. I just think that's cool. Like you can make it so your body, so your center of mass isn't in your body. How cool. So for thin plates, we're going to say that the center of mass, or the centroid, again, centroid, if the density is uniform, is x bar comma y bar, which is going to be the moment around the y-axis divided by the mass, comma, the moment around the x-axis divided by the mass. And yes, those are in the correct order. This x coordinate of the centroid is the tendency to swing around the y-axis divided by the mass, which is what we did before, right? When we did the fulcrum thing, that fulcrum was really over at where the y-axis would have been, not the x-axis, right? If we think about it like this way, right, we're kind of thinking of, oh yeah, this is kind of like our y-axis, and we're thinking, how far are we from the y-axis? That's giving you the lever arm distance. So the moment around the y-axis is calculating the x coordinate of the center of mass, or the centroid. All right, so here's the thought process. And I do want to write this down. We're going to think of that plate as a door attached to the y-axis for the moment. Not the moment, but for now. Sorry, I couldn't help it. My, or the quote-unquote moment about the y-axis, measures the tendency, sure, it's not a spelling class, for the door to swing about the y-axis. And similarly, mx measures the tendency to swing about the x-axis. So, but for mx, you'd have to be attached to the x-axis. Mx measures tendency to swing or rotate, or whatever word you want to use, about the x-axis. So one other thing I will mention here is that when using the word moment a lot, you might be kind of thinking something like along the lines of the moment of inertia. And that is actually very related to this concept, except it's not the lever arm times the mass. It's the lever arm squared times the mass. That comes up later, not in this class. The moment of inertia is the second moment. Your distance squared, that's 2 is from the second power there. So this calculation is also very related to how you calculate the moment of inertia for some object. It's kind of neat. All right, so here's how we're going to do this. This is where things do get a little bit dicey. So draw a picture again. And we're thinking about going around the y-axis here. So we're going around this way. So we want to find our mass of a strip multiplied by the lever arm. And if we're doing it that way, we want our strip that we draw to have a uniform distance from the lever arm. So if I'm going around the y-axis, I need to be using a vertical strip. There's my vertical strip. And it's a distance of x away from my axis of rotation. Again, I don't really need it. So this is y equals root x. This is y equals x. Sure. So yes,
Why are you rotating around the y-axis?
because I'm trying to find the moment around the wax. I'm gonna do both, but I'm first trying to find the x bar component, which is the moment around the y-axis divided by the mass. So for this mass, so let's find the moment of our strip. I suppose I should use capital M. So that's going to be the mass of our strip times the lever arm. So that strip, its mass is, well, again, we're really talking centroid here. The density is uniform. When they say the density is uniform, I just pretend like it's 1, even if they say it's 2, because it doesn't actually end up mattering because it cancels out in the whole process. So the mass of my strip is going to be the area of my rectangle here. Cool. The area of my rectangle times the lever arm. That's going to equal the area of this rectangle is the top function minus the bottom function times the width dx. If you want, you can toss a delta in there for the density. Sorry, not a delta, not the delta, yeah. Sorry. You can toss in the delta for the density if you really want, but we're going to see it cancel in the end. And then the lever arm's length is just x. And if that's the moment of our strip, then to find the total moment for the whole shape plate, we're going to add up all the moments just like we've always added up all the things. We're going to integrate. So the moment around the y-axis is going to be the integral from as far left as 0 to as far right as 1 of this quantity, delta times root x minus x times x times dx. So let's calculate that. It's going to be, I'm going to pull out the delta. I have the integral of root x times x is x to the 3/2. X times x is x squared, 0 to 1 dx. We're going to get delta times the integral from 0 to 1 of this is going to be, see, 2/5 x to the 5/2 minus x cubed over 3 from 0 to 1. That's easy in that we know we're just going to get 2/5 minus 1/3. Right, because you get 1 times 2/5 minus 1 over 3 minus 0 minus 0. So we're going to get that, which is going to end up being 6/15 minus 5/15, which is 1/15. That's my moment around the y-axis. And to find the moment around the x-axis, we can do the same sort of thing. And I think I can make this work. Yeah. So for the moment around the x-axis, same idea, but instead of drawing a vertical strip, I want to draw a horizontal strip because I want my strip to have a constant distance away from the axis so it has a lever arm whose length isn't varying wildly because that becomes challenging. So going around the x-axis, here's my strip, here's my lever arm, and it's going to be the same idea. It's going to be the integral from 0 to 1 of my density times the area of my strip, which is going to be the right function minus the left function, but things are in terms of y now. So instead of being x minus root x, it's going to be y minus y squared. The right function is x equal to y. The left function is x equal to y squared. The lever arm is y dy. Multiply it out. Y times y is y squared. Y squared times y is y cubed. Integrate. Y to the 3rd over 3 minus y to the 4th over 4. 0 to 1. And then we end up getting delta times 1/3 minus 1/4, which is 1/12. Okay, we're almost there. We just need to find the mass now. So the mass of the shape is just the area times the density. The area or the mass is typically the easiest part. The mass is just going to be one of these integrals without the lever arm. So you could either do it as the integral from 0 to 1 of root x minus x times delta, or y minus y squared times delta. Either way should get you the same thing. Let's do y minus y squared. That feels actually better to me. So it's going to be delta times y minus y squared dy, which is going to be giving us delta times y squared over 2 minus y cubed over 3 from 0 to 1, which is going to be delta times 1/2 minus 1/3, which is going to be 1/6 times delta, right? 3/6, yeah, delta times 1/6. Now here's why I included the delta here. Normally I would not include the delta. I'd be like, I don't need it. My density is constant. But note, look, when I find my x bar by doing my divided by the mass, or my y bar, which is going to be mx divided by the mass, when I do delta times 1/15 divided by delta times 1/6, the deltas cancel. When I do this one, delta times 1/12 divided by delta times 1/6, the deltas cancel. So you don't actually need to include that constant density in there, but it's nice to have thought about the fact that, oh yeah, we're really finding a mass and a moment, and we're dividing them, and then the densities just happen to cancel, which is why we call it a centroid, because it's just going to be the central point of the area, as opposed to something with non-uniform density that might be really heavier on one end and lighter on the other end, which we'll also see. So in this case, yeah, let's go ahead and write things so we're still there. Yeah, my center of mass, x bar comma y bar, is going to equal, so x bar is my 1/15 divided by the mass, which is 1/6, and y bar is going to be mx 1/12 divided by mass, which is 1/6. That's going to simplify to 6/15 or 2/5, comma 6/12 or 1/2. So our center of mass is a little bit left of the middle, but the height is exactly the middle. So maybe we're like right about there. Sorry, right about there. At 2/5, comma 1/2. And again, what we're saying is that's the place where you could put a finger under it and it would perfectly balance there if you could balance it, right? Like, I'm not good at balancing things. So like I can find the center of mass of this piece of paper, but I mean, right? Problems. So that's the generic idea of how we're finding centroids or centers of mass. We're finding the moments around both the y-axis and the x-axis, and then dividing those moments by the mass to get the coordinates of the center of mass. It's kind of a pain in the mass. All right, that was terrible. So let's do one more where we have a variable density. And then we'll talk, yeah, we got time. We'll talk a little bit about why this becomes extra terrible sometimes. So let's look at this next example. We want to find the center of mass of the plate below, which I'm not going to describe, I'm just going to draw. And we're given that the density now is not constant or uniform. The density, a distance of, no, we'll just say the density is x squared. And here's my region. My region is bounded below by y equals 2x and above by y equals 3 minus x squared. So we're looking at this region here. Now I would almost always start off actually by finding the mass first, because usually that's easiest. It kind of sets the tone for how things are going to go. So the mass is relatively comparatively nicer. You're just trying to essentially find the area, but you're integrating the area over or you're integrating the density over the area. So it's going to be the integral of x squared, that's my density. And then, God, this is so much easier in 21D. It feels ridiculous that we're doing it here, but okay. Because you don't have to like think about, okay, what's this? And it's just, yeah. So I'm thinking about my area being, I should have really started by saying the mass of this strip is the area of that strip multiplied by its density. And the area of that strip is the top function minus the bottom function, which is 2x minus, sorry, not 2x minus, 3 minus x squared minus 2x. The top function is 3 minus x squared. The bottom function is 2x. Yes. So that's the area of my strip. That's the density of my strip. We multiply them together, we get the mass of the strip. And then we add up all the masses of the strips to get the total mass of the plate. My strips go as far left as 0 and as far right as whatever this point of intersection is, which looks like it's probably going to be x equal to 1. Because if x is 1, both of the y's are equal to 2. So here, if we multiply it out, we get the integral from 0 to 1 of x squared times 3. That is a 3. I know it looks gross. Sorry. X squared times x squared and x squared times minus 2x. And then we calculate it, and we end up getting x cubed minus x to the 5th over 5 minus 2x to the 4th over 4, which is x to the 4th over 2, 0 to 1. So we get 1 minus 1/5 minus 1/2, which is going to be 10 tenths minus 2 tenths minus 5 tenths, which is 3 tenths. So there's our mass. Okay, looking good so far. Let's find the moment around the y-axis since we've already got a vertical strip. Yeah.
What area is it the top minus bottom?
So I would say it's the top minus bottom times the width, which is dx. So the area is the height of my strip, which you exactly said correctly is top minus bottom. Or if it's a horizontal strip, right minus left, multiplied by the base, which is your dx in this case. Area of that rectangle times its density, x squared.
What's the base on the back?
So it's real, so it's right there. So it's literally just a very, very, very tiny change in x, dx. All right. So now let's find the moment around the y-axis, which is going to be, this is why I kind of like doing the mass first, because the moments are just, well, the ones that aren't terrible, are just going to be take the same integral and multiply your mass of your strip by the length of the lever arm, which if you're going to the y-axis, the length of the lever arm should be x. Right? We're going around the y-axis, so we're x away from the y-axis. So my moment around the y-axis will be calculated as the integral from 0 to 1 of x squared times my 3 minus x squared minus 2x times my x times dx. So there's my density, there's my height, there's my lever arm length, and there's my width again. Or base if you prefer. Sorry, width slash base. So practically the same thing. In fact, all I really have to do is look at my old integral and increase the power on each x by 1, and that's the new integrand. So this should end up being the integral from 0 to 1 of 3x cubed minus x to the 5th minus 2x to the 4th. Right? It's the same thing I had before, but I've just multiplied it all by x. If only it were going to be so easy for the next one. Sadly, it's not. So then we're going to get 3x to the 4th over 4 minus x to the 6th over 6 minus 2x to the 5th over 5. At least we were in luck in that our limits of integration are 0 and 1. So we get to just plug in 1 and get 3/4 minus 1/6 minus 2/5 minus 0 minus 0 minus 0, which is going to end up being, the common denominator here is going to be what, 60? Yeah, 60. So multiply that by 15 over 15. So you get 45 over 60 minus 10 over 60 minus 2 times 12 is 24 over 60. So we get 45 minus 34, which is 11 over 60. Let's check my work and see if that's right. Yes, it is. Yay. Okay, but now here's the problem. When we tried to find the moment around the x-axis, we can't really do what we did before. If I'm trying to find mx being, the integral of the mass times the lever arm times, dy. Well, I have a real problem in that I can't really do things in terms of y at all because my mass has an x squared in it for the density. And there's no changing that, right? I just can't. Like, it is x squared. There's nothing to do with y. So the problem here is that my mass is really my density, which is x squared times my area. And then my lever arm is the distance to the x-axis, which is y, d whatever. That's a problem that can't be fixed by trying to use y. So we are forced to use the variable x. But then the problem is, we're forced to use the variable x, and our strip is vertical, which it has to be if we're using dx. Our strip isn't a uniform length from the axis of rotation or the axis of lever arming around. So what do? Well, this is where things get a little bit gross, or grosser, I guess, if you want to say, because it's already kind of gross. So here's the general idea. Here's the alternate formula for mx. So I'm just going to draw something kind of general, and we'll talk about it. So let's say we have something, I don't really care what it looks like. It looks like this. And my top function is f of x. My bottom function is g of x. And I'm trying to figure out what the moment of this vertical strip is. So I said something before that's kind of useful. For circles and squares and rectangles, the center of those things, the centroid, is the center. Now, I know we're talking about center of mass here, but what we can think about is that if we think about all of this mass being just placed at its very center, it's like we have not really changed anything at all, because we're just saying, okay, now instead of all this mass being distributed along here and having some moment, we can pretend like all of the mass is at this one point that is the center of mass of that object. I know it feels a little bit like I'm just telling lies, because it's like, why can you do that? Because it works. Because the physics works, the math works. We can pretend like, in fact, we do this all the time where we say, like, in this system, we're going to pretend like this large object, it's really just this point, and all of its mass is concentrated at that point that's its center. And we're allowed to do that because it works. If you want a better explanation, ask a physicist, because it's not me. But what that means is we can pretend like our lever arm is the distance to the center of that rectangle. So here our, let me write this down. Our mx is just like before. It's still the mass multiplied by the lever arm. Our mass is still our density times our area. But now our lever arm is halfway between f of x and g of x. There's a better way to say that. It's the average of f of x and g of x. So our lever arm is going to be exactly a distance of f of x plus g of x divided by 2 away from the x-axis. And then, so we don't just leave it like this, though, because check out what happens. The area there is our, well, just like you said before, there's the top minus the bottom. That's our height times our dx. So we get f of x minus g of x. And then we have our f of x plus g of x divided by 2, and then put the dx out here. And then when you have f minus g times f plus g, just like a minus b times a plus b, we're going to get f squared minus g squared. So this simplifies down to something that's not the most terrible thing I've ever seen. it's going to be 1/2 times our density times f of x squared minus g of x squared. And so the moment in general around the x-axis here is going to be 1/2 the integral of our density times f of x squared minus g of x squared dx. And in a similar way, you could do the same thing if you're going around the y-axis if you needed to. So you can have, there's also an alternate formula for the moment around the y-axis, which is exactly the same idea. It's 1/2, I'll just write it down. It's moment around the y-axis would be something like 1/2 the integral of delta times, if this was say h of y and this was k of y, it'd be 1/2 k of y, sorry, h of y squared minus k of y squared dy. So this is what I was alluding to when I said it's much more terrible this way, because it's so much easier if you just use a double integral. But we don't learn about that until later. So yeah, I know it's rough. Hopefully, I don't know, maybe you won't have to memorize these formulas. Maybe they'll just be given to you. Sometimes people give them to you, sometimes they don't. I don't know. Babson seems like he gives you a lot of formulas, so he might give these formulas to you. That doesn't mean it's easier to calculate. It just means you don't have to remember that part at least. So back to the problem we were doing, which is this region over here. We can now calculate our moment around the x-axis as 1/2 the integral from 0 to 1, our density times our top function, which is 3 minus x squared, minus our bottom function, which is 2x squared dx. That is the moment around the x-axis, and it is kind of gross. So let's do it. Do we need to do it? Yeah, we need to do it. All right, so we're gonna get 1/2 times the integral from 0 to 1 of x squared times 3 minus x squared is 9 minus 6x squared plus x to the 4th minus 4x squared dx. We're going to simplify that a bit. We're going to say it's 9x squared. Minus 6 minus 4 is minus 10. So minus 10x squared times x squared is minus 10x to the 4th. And then x squared times x to the 4th is x to the 6th. Well, the numbers get gross fast in these problems. So then we're going to have 1/2 times 9x cubed over 3 minus 10x to the 5th over 5 plus x to the 7th over 7. We're still lucky in that we have 0 to 1. So we're going to get 1/2 times 9 over 3 minus 10 over 5 plus 1 over 7. Okay, that wasn't too bad. So it's 1/2 times 1 plus 1/7, which is 8/7. So it's 1/2 times 8 over 7, which is 4 over 7. And finally, we can now calculate the centers of mass, the center of mass by saying our x bar comma y bar is going to equal the moment around the y divided by the mass, comma, the moment around the x divided by the mass, which was, let's see, the moment around the y was, I forgot what it was. I think it was 11 over 60. Somewhere. Yes, 11 over 60 divided by the mass, which was 3/10. And the moment around the x was 4 over 7 divided by 3/10. So if we calculate this, it's going to be terrible. It's going to be 110 over 18, comma, 40 over 21. And I guess you could reduce that to 55 over 9. Seems really big. 110 over 18? 110 over... That does seem really big. Oh, it was 11 over 60, not 11 over 6. There we go. Okay, much better. 55 over 90, which is going to be 11 over 18. So why was I so worried? Well, 55 over 9 is like 6. And if you look back at the shape we were drawing, an x coordinate of 6, it'd be way over here. It does not seem like that's where the center of mass would be. So, but we have a reasonable answer. 5 over oh, sorry, 11 over 18 is less than 1, bigger than a half, and 40 over 21 is just a tiny bit bigger than 2. So we're somewhere around here-ish, which seems plausible considering the density gets more dense as we move further to the right. It'd be very different if it was a uniform density or if it was a different density function. All right, how much more can we subject ourselves to? So let me ask you all a question. Did Babson talk about Pappus's theorem? Okay. All right, so yeah, we'll subject ourselves to the full torture. So let's do one more thing, and then we'll talk about Pappus's theorem for a brief moment. So one more centroid. It is a centroid. So when I say find the centroid, it means you get to assume, you should assume density is 1. So you don't really think about writing the density at all. So find the centroid of the region bounded by y equals sine x and y equals 0, where x goes from 0 to pi. Sorry, 0 to 2 pi, apologies. Sorry, no, 0 to pi. Yeah, I meant pi. So meaning we only want one like hump of the sine function. We don't want more pieces of it. So we're looking at something like this. Where that's the point pi comma 0, and this is the point pi over 2 comma 1. And I'm going to cheat a little. I'm going to say, great, I already know the coordinate of the x part. X bar is equal to pi over 2. Because symmetry, right? This sine function, this left half is exactly the mirror image of this right half. So we definitely have symmetry about the line x equal to pi over 2. So we can definitely assume that our centroid lives somewhere on that x equals pi over 2 line. We don't know what the y coordinate is yet, but we know what the x coordinate is for sure. But now for the y coordinate, we do have to use the not fun version of the formula. Because again, well, it's kind of really hard to do a horizontal strip here. The right function is x equals arc sine of y. The left function is also x equals arc sine of y. No, we have to use the alternate formula. So to find the y bar, which is going to be mx over the mass. So our mass, which is just our area, because our density is 1, is going to be the integral from 0 to pi of sine of x. No big deal. That's just going to be negative cosine of x from 0 to pi. That's negative cosine of pi minus negative cosine of 0, which is negative negative 1 plus 1. So our mass is 2, or 2 times whatever the uniform density is, but that density is going to cancel out when I try to find y bar. And then my moment around the x is going to be, okay, I'm going to use that formula. So it's going to be 1/2 the integral from his left is 0 to his right is pi of my top function squared minus my bottom function squared. Do be careful. You have to do the squaring before the subtracting. Here it doesn't matter because we're subtracting 0, but make sure you're doing the squaring before the subtracting. So it's going to be sine of x squared minus 0 squared. Which we didn't need to write the 0 squared, but okay. All right, who remembers how to integrate sine squared of x? Remembers what trig identity we have to use to integrate sine squared of x? I know. So it's 1/2 the integral sine squared of x is equal to 1 minus cosine of 2x divided by 2. I know it's been a while since we've seen that one. I'd pull out the 1/2, so I write this as 1/4, and then the integral of 1 is x. The integral of cosine of 2x is sine of 2x divided by 2. From 0 to pi, we plug in pi and we get 1/4 times pi minus sine of 2 pi is 0. minus 1/4 times 0 minus sine of 0 is 0. So we end up getting pi over 4. I know I did that kind of fast, but it is correct. Double check. Yep, looks right. Cool. So then our y bar is going to be the mx we just calculated divided by the mass we calculated, which is going to be pi over 8, which is a little less than 1/2. So it's actually more like it's down here, which again, considering there's more area lower than there is higher, it would make sense that the center of mass was below 1/2, not above 1/2. Right? We're really thinking of, in this case, the center of mass dividing half the area on top and half the area on the bottom, and half the area on the left and half the area on the right. And that's what it's doing here when the density is uniform. So our center of mass here would be x bar comma y bar is equal to pi over 2 comma pi over 8. I would say it's not a bad idea to do the work to find the center of mass coordinate for x bar the long way, just to show yourself that you really do get the right value. So if you wanted to, you could certainly calculate my, and you should get my equal to pi. So my would be the integral from 0 to pi of your lever arm x times your sine x minus 0 dx. And you could certainly do that using integration by parts, and you would expect to get that equal to, I believe it should equal pi, because then pi divided by 2 would give you the coordinate of the x bar. You should do it. Not right now, but later. I really, really like, it's not a bad idea. It's not that hard to do. You should totally do it. I'm not going to do it though. You should do it. All right, let's subject ourselves to the torture of Pappus' theorem for a minute, and then we will be done. So what is Pappus' theorem really about? It's about finding a volume a different way. I should be more specific. It's about finding a volume of revolution a different way. So normally, way back when we talked about finding volumes using like the disk or the washer or the shell method, more disk washer, less shell, we could find the volume of that same region of the solid formed when we revolve that previous region around the x-axis. And we're just going to do this the regular way to start off with, just to show us that we do actually get the right answer, whether we do it this way or we use Pappus' theorem. So doing it the old school way, here's our sine function. And we know that if we rotate this around that axis, we're going to be using the disk method. Well, I guess we could use disk or shell, but shell would be terrible for the same reason we didn't do mx the nice way in that previous problem. So I'm thinking about a vertical strip, and then I know that my volume of my strip is going to equal pi times the radius squared times the thickness of the strip. My radius is just the height of the function, so it's pi times sine of x squared dx. And so then we're going to add up all the slices, which is going to be the integral from 0 to pi of pi times sine squared of x dx. And just like last time, integrating sine squared is exactly the same as it was before. So it's going to be pi times the integral from 0 to pi of 1/2 times 1 minus cosine of 2x. So we get pi over 2, bring the 1/2 out, we integrate, we get x minus sine of 2x over 2, from 0 to pi. The nice thing about this integral is most of the time the things you're plugging into the sine function end up making sine equal to 0. Not always, but a lot. So here we get pi over 2 times pi minus 0 minus 0 minus 0. So you end up getting pi squared over 2. So a little bit more than 4.5, right? Because pi squared is a little more than that. Okay, So the idea with Pappus's theorem is that instead of doing this, if you know the area of the region and you know the centroid of the region, you can think of that area all being concentrated at the centroid, and then you're going to take that area and multiply it by the length it travels when you rotate the centroid around the axis, which is the circumference of the circle located at the center. So let me draw you a picture. I know I said a lot of words here. So here's the idea. The idea is that instead of doing all that, we can pretend like this region here, same function, right? Equal sine of x. Here's my centroid right there at pi over 2 comma pi over 8. And we're going to pretend like the entirety of the area of this region was how much? It was a nice number. It was 2. So the area is equal to 2. And if we imagine all that area centered right there and then rotate this all the way around the x-axis, that centroid is going to travel the circumference of that circle. The circumference of that circle is 2 pi times that circle's radius, and that radius is just, in this case, pi over 8, the y coordinate of the centroid. So the area is 2, the distance traveled is going to be the circumference, which is 2 pi times pi over 8. Right? Radius to the centroid, essentially. Or the distance between the centroid and the axis of rotation, if you like. And then if we multiply the area times the distance it travels, it's kind of like taking an area like this and saying it's going to travel like this far. The volume you would get would be exactly the area of this sheet of paper times the length it traveled. Same idea here, it's just we're not traveling in a straight line. So, but if we multiply these together, let's see, we get area times distance traveled is going to equal 2 times 2 pi times pi over 8. Pi times pi is pi squared, and 2 times 2 is 4, divided by 8 is divided by 2. I think that's what we got before. It sure is. Look at that. Pi squared over 2. So that's the gist of Pappus's theorem, is that you can calculate the volume instead of by doing the shell or the washer method by finding the centroid. Why would you do that? Well, you would do that if it was easy to do or you'd already done it. So if someone asks you to find the volume, you shouldn't jump straight to Pappus's theorem. You should be like, oh, someone already told me the centroid. Cool, I can do it easily. Or no, or you already found it because you were doing that work anyway. And then someone at the end said find the volume. You're like, okay, well, I might as well use Pappus's theorem. One of the interesting things, I think people often ask this question about, like, you can find like the volume of a torus or a donut really easily. So for example, if you have a torus by, say, taking this circle, let's say the circle has a radius of 1 and it's centered at a distance of 3 from the axis of rotation. So that point there is 3 comma 0. Then the volume of the donut you would get by rotating that circle around the y-axis, well, the centroid of a circle is super easy. It's just where its center is. So this is going to, can I draw this? Maybe. I didn't really give myself enough room here. Go all the way around like that. Around like that, all the way around like that. So we're getting this donut shape, and the volume of this torus is going to be, well, it's the area of the region. Well, that's easy. It's pi times the radius of that circle squared. So that's the area of my circle. And then the distance it travels is the distance its centroid travels. Its centroid is exactly 3 away from the axis of rotation. So the distance it travels is going to be 2 times pi times 3. The circumference of the circle along the path it travels. And that's going to end up giving us 6 times pi squared. So it's nice when you have a nice shape whose area and centroid are easy to find, because then you can answer a question like this relatively easily. Yeah, that's kind of it. There's not a lot more to say about Pappus's theorem, and I don't want to say a lot more about Pappus's theorem. Yeah, So yeah, let's end it there. So I would say this is the end of talking about physics in this class. Unless you have more questions about it. I'm happy is the wrong word. I'm willing to talk about it and happy to help you with it. But as you might have gathered, it's not my forte. This is not what I am best at. So we will try to leave it behind. But again, if you do have more questions about it, please don't hesitate to come ask in office hours or ask in class if you want to. Hey, James, can we look at the centroid formula again, or the center of mass, or any of the moments or things? I'm really more than happy to help you with it. Just not happy to do it on my own. Because the calculations are gross. They're always gross. It just becomes super messy. So yeah. Anyway, have a lovely rest of the day. I'll see you all next week or tomorrow in office hours.